All right, so let's take a look at today's lesson. We're going to be adding three new theorems, actually four new theorems. Okay, and I'm just going to talk about those for a moment, and we're going to practice. You also, when you're solving some of the problems, many of the other theorems will come up along the way. And the same process, what I want you to do is, as you're going through the question, then you're writing down all the supporting theorems that you're using. Okay, so these are the new theorems. The first one is called perpendicular bisector theorem. And that theorem says that if we have from a radius, this is a diameter here, if a radius goes perpendicular to a chord, which we can see here, okay, then it will bisect that chord exactly. And also, if we don't know the angle, but we know that there's a radius that's bisecting a chord, then from that we could say, okay, well, we know that these lines are perpendicular. Another thing to notice is these angles here. These are congruent, so the arc angles LB and MB are also congruent. Okay, so let's look at the example here. So here we have a radius and it's perpendicular. So we know that these are bisect. AB is bisected, so AD and DB are congruent. And so from that, we know that this must be 4. Okay. What do we have? Well, we have a right triangle. So how can I find the radius with the right triangle? Pythagorean's theorem says, well, we square the legs, so 3 squared plus 4 squared is equal to the hypotenuse squared. So that would be 25. The square root of 25 is 5. So this is 5, right? Just scrolling down. The next theorem, this one's a little bit more challenging. Once you learn the shortcut of this theorem, it's really simple, but talking about why it's true, okay? So it's called the intersecting chords theorem, and we may have seen some intersecting chords before. And right away we can see, well, we know the vertical angles are congruent. So this angle here and this angle here, those are congruent. And what that theorem says is that if we multiply, to take the product of the two segment lengths in each chord, so DE times EB, that will equal to the product of the two segments in the other chord. Now, why is this true? Well, let's take a look at the chord I just highlighted here. And we know that angles subtended on an arc from the same chord are congruent. So these two angles are congruent. And we already said that the vertical angles are congruent. So by angle similarity, we know those triangles are similar. Okay, so let's look at the similar triangles. If we look at those ratios, they're all equals because they're proportional. So they're proportional triangles, and then we can make all these ratios here. So for example, the small side of the one triangle to the small side of the other is equal to the big side to the big side, or the small to the big on this triangle is equal to the small to the big on this triangle, etc. And what that translates to is a shortcut we can see if we simplify these ratios, that the products of the segments are equal. Okay, so let's look at over here as an example. We've got two chords intersecting, and so we know the product of their segments are equal. So we can say that, well, 8 times 7 is 56, and then here we have 14x. So 14x, right, is equal to, forgive me, my drawing's terrible, 56. So that's leaving us with the x is equal to, I believe it's 4. X is 4. Okay? And moving on. So those are our first two theorems. And then notice that this is a segment. These are all segment theorems, so not so much with the angles. Okay? This is called the secant theorem. We haven't used that word secant very much, but a secant is kind of like a chord that just keeps continuing through the triangle, or through this circle, pardon me. And the shortcut to this theorem is that if we take the intersection point of the two secants to the short side of the chord, and then take that and multiply it by the whole length here from the intersection to the far side of the chord, that will equal the same in the other secant. So again, C times D, that's going to be equal to A times B, which is relatively simple. Okay, now let's talk about why that's true. So we know right away that first of all, what I did is I took those, I took that same drawing there, I'll show it, and what I did is I created triangles here. And when I do that, I create these triangles, we know right away that this angle is shared by those two triangles. Now, the two triangles I'm talking about are this one here, and then the other one, which is right here. Okay, those are our two triangles, right? And so also, if we just look at the two chords so this is a chord here, we can see that those angles have to be congruent. So we have angle, angle, similarity. So those two triangles are congruent, and so we know that they're proportional. And if they're proportional, we can do a bunch of work and eventually come to the point where we see, just like we did before in other exercise, and these are all the ratios that are equal, is that A times B is equal to C times D. Okay, and so let's look at that. So here we have, we'll call this X. We don't know what it is. So 10X is equal to, and then we have to multiply, what is, sorry, let's see, that was wrong, okay. So we have 10 times, let's say, X plus 10. This is really hard to draw. Equals, and then we have, what would that be? 20, 9 times 20. So the small times the whole thing, 9 times 20 is 180. Okay. So we have 10x plus 100. This is slower than slow. Equals 180. All right. And so if we simplify that out, x is equal to 8. Let's see if that's reasonable. X equals 8. Okay. Okay. Let's think. Does that look like it's reasonable? I would say so, yes. Okay. Seems to be reasonable. Let's move on to the last theorem, which is actually very similar to the previous one. And it says that, okay, we have a secant and a tangent, the secant-tangent theorem. And here we can see, okay, well, again, we have this product of the short and the full length. And then we have just c squared over here. Well, that's a little bit different because this is a tangent. But it's the same as the previous theorem, except that if we started with a secant here, we would have the short length and the long length. However, as we move that secant out and it becomes a tangent, C and D become closer and closer together, the short and the long, until they become one. So instead of C times D, it's just C times C because they are equal. All right, C and D are equal, so we can say it's C squared. So let's go ahead and I've given you a question here that's going to bring you back to some memories of previous units. So we've got y times that whole length, which is y plus 30. Oh, you can see right now this is going to be a quadratic. is equal to, and then we're going to square this side 400. Okay. So I'll let you work that one out. You're going to get two, it's the easy roots, and you need to rule out, obviously, the negative one because it's not going to, you can't have a negative length. Okay. So